through. Determinants are going to be used to help solve systems of equations. It is I'm trying to think of a better way of describing it. It's a way to manipulate the numbers within a matrix that is helpful. You can take determinants, and I'll show you guys how to use it to determinant to find the area of a triangle given ordered pairs. It's a formula that you guys probably wish you would have known a long time ago. They do not take long to work with. It's just a matter of following the pattern. So,
You set up one.
did?
Yeah.
What? Wouldn't it be? Wouldn't we all have to determine if it was funny?
I think it would be determined no. Yeah. Make a Seinfeld joke.
Anyway, so using a determinant, this is nothing more than multiplying diagonals and multiplying, adding, subtracting diagonals. What happens is if you take a matrix and you write the determinant of matrix 1, 2, 3, 4. If I want to say find the determinant of matrix 1, 2, 3, 4, this is a 2 by 2. Determinants will only work with 2 by 2s. This will sometimes be written as determinant for DET, or they'll write it like this: uprights. So it looks kind of like an absolute value, but those two upright bars stand for a determinant. All right? They both mean the same thing. All you do is multiply the downward diagonals first, 1 times 4, and to that you subtract the upward multiplied diagonals. So what's 1 times 4? 4. What's 3 times 2? What's 4 minus 6? There's your determinant for that value.
It's all a trap.
It's not a trap.
It's a sham.
It's not a shamocker. It's a trebuchanocker.
I need sham off now.
Okay? All you do in a 2 by 2 matrix to start, perhaps we're starting with the small stuff, is that you start with your downward diagonal, multiply together, subtract the upward diagonal. That's it.
But wait.
Hold on, you guys just worry too
Cynical
much.
people. What do you expect?
And it slices, it dices, it julienne scribes.
Are we honest to tell you for that one?
Yeah, if it's the uprights like that, it's just automatically you're doing determinant. Okay, like I said, it might just say find the determinant of the following matrix. It could say DET of a matrix, or it could be upright. They all mean the same. It's always down first. It's always down. I see what you're saying. I see what you're saying. It's if you can when you get to the larger ones, it's easier to remember. If you want to continuously work your way down before you work your way up. It's not completely wrong, but it helps keep it straight. Trust me, if it's going downward and then upward. Okay. So this one, all you have to do is 1 times 5 minus 2 times 3, and you get.
Told you I was right, man. You were wrong.
Okay.
Wait, so you can use this to solve the equation?
Yes.
That makes me really mad. Why didn't we?
Oh.
Wait, what?
We didn't do this unit.
You said, why didn't you use this to solve
You don't
systems
need a
of
unit
equations?
to do this. You just cross, like, multiply.
This is one step in doing the system of equations. But you use this idea of a determinant multiple times, and you see how rather quickly it is to get a determinant. That's how you're able to solve them through. And we'll solve systems tomorrow with determinants. Today I just want to work on determinants.
If I would have known this,
Okay.
I would have been safe that extra credit question on the afternoon last year. They screwed me over.
Not so much what we did yesterday with the multiplying. The multiplying is just a big pain in the butt.
Yes, agreed.
So let's look at the 3 by 3 stuff. The scarier stuff. Speaking of scary, how are you?
Good, how are you?
Oh, great, good to see you. You stay out of trouble. Hey Jay.
Yeah?
So here's where things get a little interesting.
Oh yeah.
When you have 3 by 3s, Okay?
Yeah, man.
Well, we're starting with the 2 by 2s. In a 3 by 3, I'm not even going to bother looking at all those definitions up because it's a pain. What I want to do is look at just this matrix. I'm going to find the determinant of that matrix. So take a second and write that out. I'm going to show you a nice little trick to get all of your downward and then all of your upward diagonals. It is a very easy system to follow. Okay? Once again, we always start with all of our downward diagonals. So I'm going to start with the large downward diagonal. Four, 1, and 5. Okay? Now, here's where it starts to get a little interesting. What I want to do is I want to create another 3 of them in a row. So what I do here is the following. I'm going to take this column and just rewrite it here.
Is a separate matrix?
No.
Oh.
And then I'm going to take because now I have another downward diagonal of 3 in a row.
That seems made up.
That does seem that.
It seems like just some guys like, you know, I'm just gonna find the easy way out.
I'm going to show you the other way. Like, there's 2 ways of doing this. This is one way that a lot of people so far today have agreed with me completely. That's very simple. There's another one that's less visual that works the same way. Yes, Aaron? Yes, because now I'm going to take the second column and do it again. Because now I can take it and get the last of the 3 downward diagonals.
Start to flush yourself a little bit. Making sense.
What's happening here, if you want to see it in 2 different ways, is that I'm taking, I'm taking this matrix, and the first thing I'm doing is I'm multiplying the downward 3. Then I'm taking these 2 with this one. Then I'm taking this one with those 2. I'm creating the 3 downward ones just by moving these 2 columns outside. It does nothing to the problem. It's easier to visualize. Yes, ma'am.
Why in the last one are we subtracting the downward and
Because I'm adding all 3 of the downward diagonals together, and I'm going to get some number.
okay.
That's my first step.
Okay.
So I have 4 times 1 times 5, which is 20, plus 0, plus 6. So all of my downward diagonals equal 26. Emma, put it away. Please, trust me. You're going to want to watch this. And now to this, I'm going to subtract all the upward diagonals.
We have to do the same exact process.
Yes, but going the other direction. And that's why it's not a bad idea to write it out this way, because you're going to see all 3 of them quicker. It's just easier to see. That's all. So when I go and work the upwards, 2, 1, negative 1, plus negative 3, 0, and 4, and then 5, 1, 2. It's the same process every time. Yes, sir.
Shouldn't the first one be 23, not 26?
Thank you. I saw the 2 and the 3. I thought it was for some reason. Okay. So then what I'm doing here is I'm going to subtract now the sum of all the upward diagonals. So I have negative 2, 0, and 10. What are all those out of people? 8. So my determinant is going to equal the downward diagonals minus the upward diagonals. I'm done. It looks weirder than it really is. It's just a matter of how you want to organize it. Either way is fine by me, because notice, all I'm doing is taking the downwards and then taking the upwards. It's the same values, just sometimes people rather see it written like that with the extra 2 columns outside because it's easier to click them together. That's all. It's the only difference between the two. Whether or not you want to write it out an extra 2 columns or just deal with it within the matrix. That's all we're doing. Bless you. And if there was a 4x4, we'd have other ones to go. That's it. These only work for square matrices. Okay? And the reason they're only going to work for square matrices is when we have systems of equations, you're going to have 2 variables and an answer. And it works itself through. You'll have coefficient matrices, solution matrices, and they all work with determinants. Huh.
I'm not buying it still.
What is this, crazy that you don't believe that's going to work?
No, that there's multiple types of matrices.
Yeah.
There's one.
Well, there's one generic matrix, but there's different matrices that you can use.
That's where Neo is, that's it.
So take a second and try this. Try and see if you want to rewrite it with the 2 columns going on the outside, or just go with it right through there. Always start with the downward diagonals first, then work your way up. It's like the game Chutes and Ladders. You have to go down the chutes before you go up the ladders.
I love that game. I always win.
That was very punny on my part. Yep.
I don't even remember who played it.
And you get used to it over time. If you do a couple of them, it's the same process each and every time. Did you really?
Yeah.
Oh boy.
Just wait till I'm done. That's going slow instead.
I was always right.
Oh, wait a minute.
I like your code.
I got it.
So I have my downward diagonals. Oops.
Oh, no.
My downward diagonals 2, 0, 4, negative 1, 1, and 1, 3, negative 2, and 2. Those are all my downwards. I get 0, negative 1, negative 12. So this is negative 13.
This one was.
Great so far.
I love this machine.
No, you don't.
So all of my downward diagonals get me at negative 13. I go the other direction. Wait, what?
So you got that far wrong.
0, negative 1, and negative 12?
Why would it be
There's a
negative
0 in
0 plus negative 1 plus negative 12.
Oh, I wrote down the wrong thing.
There's a 0 in there.
Upward.
I wrote down the wrong numbers.
1, 0, and 3. 2, 1, and 2. 4, negative 2, negative 1.
I figured out why I did it wrong.
So I have 0 plus 4 plus 8.
These zeros are killing me.
So 4 plus 8 is, so my determinant becomes negative 13 minus 12, which is negative 5. And this has been asked earlier today, will determinants always be negative? No, just so happened that it was dumb luck that we had 2 negatives in a row.
You said that just seconds before I was going to ask it.
It's a dumb look.
Well, gee, do you think I know the questions you're going to ask? Maybe I do. Determinants. No, we're not.
Oh.
But they're not bad though, are they?
No. Well.
What were you gonna ask? We'll use determinants with Kramer's rule tomorrow. That gets to be a little bit messier, but it's not like it's more complicated. It's the same complexity of this. The usefulness of determinants, though, it allows you to find the area of triangle if you have ordered pairs.
Why would I do that?
Well, if you were just given ordered pairs and you had to find the area of triangle, you used to have to do a long way of doing it. There was one way we did it with trig, which I don't remember, but I do remember how to use a determinant. If you have 3 ordered pairs, you're going to get somewhat of a matrix. Here's what we do. Whenever I want to get and find the area of a triangle, and I have 3 ordered pairs, the first thing I do is going to put them in columns. 1, 2, 6, 2, 4, and 0. I put the x's in a column, the y's in a column, but now notice I can only use determinants if it's a square matrix, which means I need to create another column. Well, if I'm multiplying things together, what's the number I multiply them by that doesn't change them? Ones.
1 and 3, right?
Nope, you just put ones all the way down.
Oh.
Because that column won't change anything. It's like a dummy column.
Oh, I thought you had to like multiply it, so it's like a 2 by 1, or like.
Oh, I see what you're saying. No. In this case, we're using the determinant of that matrix. So I'm creating a square matrix by putting a column of 1 in there. It has no bearing to the problem.
Okay.
So now what I do is I find the determinant of this. That's why I put those uprights up. And to that, I'm going to multiply it by either positive or a negative 1/2. Whatever the value of the determinant is, I take half of it, and then I have to change the sign to always make it positive. Because can area ever be negative?
No.
That's the only rule that they give you. So now you get these ordered pairs that are so easy to work with. As you work down your diagonals, you have, let's see, 1, 2, and a 1, plus 2, 1, 4, plus 1, 6, oops, 0. Well, that's 2 plus 4, which is 6. My downward diagonals equal 6. My upward diagonals would be 4, 2, 1, 0, 1, 1, and 1, 6, 2. You guys okay without me drawing the lines in?
Yeah.
Yeah.
So we have 8 plus 12, which is 20.
2.
So my determinant will be 6 minus 20, and I can multiply that by a positive or negative 1/2.
Take a guess.
Yes, sir.
Wait, shouldn't it be 10 instead of 6?
I added, didn't I? Thank you. Sorry. I didn't do that earlier. 2 plus 8 is 10, ladies and gentlemen, not 6.
I'm not buying this.
I know, I'm sorry that I had to math that for you, but I've mathed that.
Stop using your upper level math skills on us. Don't get it.
I'll bring it down a couple notches. So what's 10 minus 20? So do you have to multiply by positive or negative half? What's your answer then? The area of this triangle is 5. Something squared.
Is that Kramer's rule?
No, that's just using the determinant to solve
Oh,
the
that's
area of
just,
triangle.
okay, I thought.
That's all that is.
Okay.
And I think I've seen questions like this before, like on ACTs and all, where they give you, hey, here's the 3 ordered pairs, what's the area? Before you have to get distances, you have to find the heights and all that. This one isn't all that bad because they're giving you a graph. You can count. Here's a base. 1 little, 2 little, 3 little spots, 4 little, 5. And then the height was 1 little, 2 little. So it's 1/2 of 5 by 2, which is? Well, because they're not always giving you horizontal vertical. Well, yeah, it's easier, but I'm showing you how it works. Yes, ma'am.
I count the spaces.
No, you did. We did. Guys, question. Question was, did you just leave your answer? No, because what we're doing here is we figure out the order box here. We have, this is negative 10. So in order to get a positive value, am I going to multiply it by positive or a negative half?
Negative.
Is positive times negative positive or negative times negative positive?
No.
That's what I'm looking at, Ellen. So I have it multiplied by a negative half, and that's where I get 5 is my answer. That's all it is. The answer is 5. Units squared. I don't care if you label it.
You can't count squares. That doesn't.
I
thought it was.
Hey, this isn't chemistry. This is just math. It's not chemistry.
Didn't you
Nope.
just say that your wife taught you how to use matrix?
I did. Yes.
Did she teach chemistry?
Yes, she does.
Did she teach you about civil area?
What's that?
Did you learn something about?
No, she asked me about something with logarithms and why the hell they exist, is how she put it. And I had oh. I guess pH is just a base. It's a base logarithm.
Yeah.
So look at that, you got something new to learn.
Yeah, there's.
Yeah, and that's,
I know.
you gotta love the fact that you know how to press buttons now, right?
What did you guys learn in sovereign?
All right, find the area of this triangle with those ordered pairs, please. Find the area of the triangle with those ordered pairs. -4 and 2, 3 and -1, -2 and 2, -4. There's no point. There's no reason. Because they're not horizontal and vertical. None of them they're not sharing anything. They're not sharing any X's or Y.
Maybe just doing that too, like both, man.
When you put that row of ones, question out right now is why we have that row of ones. The row of one, or the column of ones, I should say, is when you're using determinants, you're multiplying diagonally. If you put a column of ones there, when you multiply those numbers and you multiply it by 1, it doesn't change their values. So it's kind of like a placeholder that doesn't affect the problem, but it allows you to use the determinant because it's a 3 by 3. It creates the square. That's why we put it there. Yes, ma'am. No, it does not. As long as you line up all the X's in the same spot, the Y's in the same spot, you should be all right. It does not matter where you start your ordered pairs. It is helpful to put them all down though, and put them down correctly. They should correspond though. I should say that. So the -4 should be next to the 2.
Oh,
It doesn't matter if it's in the first row, second, or third row. That makes no bearing on the problem whatsoever.
You do this from this to find the determinant, then you cut that in half. Oh, yes.
those are right there.
Because you do the first one. You do the down ones first. It's 11.
Oh, did?
The same answer.
No, it's not.
4, -4, -6. Is it downward -6?
Suck it, man. Go back to geometry.
Upwards, we have -2, -1, 1, -2, 1, -4, 1, 3, and 2. So I have 2, 8, 6, 16.
Wait, well, it looked like you were negative to on the bottom row.
They're both negatives. Oh,
That's my P12.
no, I'm all right. Because this 1, 3, and 2 goes 1, 3, and 2, 1 down.
I got two.
Okay. So then I find out it's going to be a plus or minus 1/2. -6 minus 16. So it's -22 inside. So I multiply it by the -1/2, which gives me 11 for my area.
Why don't they just say absolute value of it?
Because you still have to take the half of it.
Just half, well, absolute value of half.
I think the reason they don't put absolute value in there because the absolute value symbols are the same as the determinant symbol.
Yeah, you're right.
Yeah.
So
Our teacher says still.
that way they just say plus or minus, and then it just, or just remember the fact that it has to be positive. Area is positive. Not so scary, I hope.
No, that's easy.
All we're doing tonight is just some determinants and some of the area problems. I'm not going into Kramer's rule. Kramer's rule is a little bit messier. It goes into stuff where you have the linear systems. You're going to make coefficient matrices, solution matrices, some substitutions. It's very, very easy once you get the process down. So.
For modification of
I'm not normally.
Will we ever have to go above 35 degrees?
I don't know, maybe.
Not
Those are,
for multiplication.
I don't know, maybe. You should be able to fly right through these. These don't take very long. They really don't. A lot of people got a lot of them done.
Where
Where are you going?
I really want to use the electric.
No, it's Friday off. You gonna be here this Friday? 3 in a row? Wow. That's an Iron Man streak there.